Проверьте, меня слышно? Там трансляция. Okay, so the next step I wanted to speak about, to talk about Lee-Colchin theorem, which tells you that in more general settings, how to trigonalize matrices in more general setting. So Lee-Colchin theorem. So here it will be it will be the following. Actually, Lee-Colchin theorem is just for those who know something or heard something about this structural theorems. So this will be some kind of this theorem is a special case of the so-called Borel fixed point theorem. But the problem is that in order to prove Borel fixed point theorem, you should know something about solvable groups. And just getting this to get this information, you should apply Lee-Colchin theorem. So that's why. So I plan to speak first about Lee-Colchin theorem. Then just I want to maybe I shall formulate also Borel fixed point theorem, and so maybe I shall prove first Lee-Colchin theorem, and then we shall be speaking about Borel fixed point theorem. So Lee-Colchin theorem is the following. So it is the criterion how you can trigonalize the group, when you can trigonalize the group. So notice, so the easy remark, of course, that I forget to do, that if T, so the triangular group, is a solvable algebraic group. So solvable algebraic group. And the reason for that, that if you are taking you prove it by taking the corresponding commutants of the matrices and see that there are more and more zero entries that appear, and so let us refer as the exercise. Solvable means that the series of the commutants, so you can consider this series of the commutants. So then you consider G2, etc., Gi, and this series stabilizes at the unit. So that Gi is just the commutant of the previous ones. These are
of the previous two.
Yes, the previous two subgroups.
So it's about lower central, как нижний центральный ряд с G каждый ряд коммутирует, а тут.
Да, it's not the case of nilpotent groups where you can have lower central series, and so here you are commuting with this one. But for in a triangular group, you just you reduce it to the following. So the commutant of triangular group is unipotent, as we have already observed. So this is unipotent matrices, and actually, so if you take unipotent, and this is nilpotent group, so you is a nilpotent group. So the series that are stabilizers, so these are the following. So the series of this form so where you take the commutant of the previous group with the whole group, so this just ends at the unit element. Yeah? So the theorem is the following. So suppose G. So here from the beginning you can think of that you are sitting in some representation. So G here is connected solvable algebraic group. Subgroup in GLV, so that then G has a semi-invariant vector. So has a semi-invariant vector. So the action of GV is lambda that depends on G for any G. And so this can be viewed as a fixed point. So this is fixed point in projectivization. Yes, so that if you think of the line spanned by this vector in this projective space, so this will be a fixed point of a G in the corresponding projective space. Yeah? So because the vector just sends to the is sent to the proportional vector. So. Yes. It is eigenvector for all G's, where lambda G is some number. Yes.
And GLV itself is not solvable.
GLV is not solvable, but this is yeah.
That's
So
the question. So how does this happen?
yes, because it is
of GLV on projective.
because so the commutant is SLN, and SLN is simple. Yes, so its commutant is equal to itself. Yeah, so and the lambda G is of course, so it is a number in K star, and moreover this is algebraic homomorphism. Yes, so that just lambda G is just the map from G to K. So this should be of course invertible element. Because it's non-zero, and this is homomorphism. Because this is an action, we have already seen this before. And so this factors through G mod commutant, yeah, actually. So all such subsets are parameterized by homomorphism of this Billian group. So, and the corollary. Yeah, so of course this holds for K is algebraically closed field, which is quite important. It is. So here, just despite the fact that we have noticed that Jordan decomposition works over the perfect field, yeah, so you can consider Jordan decomposition or algebraically closed. So here it is quite important to have algebraic closed field from the beginning. So also there is corollary, so the theorem that if you have G is connected solvable subgroup, connected then it can be put to the set of triangular matrices. Then just there exists a basis such that. Что? It's one. It's the easy. It's not easy, but it is corollary of this one. So basis such that all matrices are triangular. So all matrices of G are triangular. So all elements of G are triangular matrices. Are written. Are written. Да. Ну, то есть просто вот как бы разрешимость гарантирует вложение в треугольной матрице. И это тут же говорит, что so this as the corollary that we have, so if G is connected solvable, then GU is the subgroup. The set of unipotent elements is closed algebraic subgroup. Okay. So let it be theorem 1, theorem 2. So theorem 2 follows from just theorem 1 implies theorem 2. And the reason is very simple, so that you consider, so you take V, take V1 to be eigenvector for G. So we have already done this argument. So then you consider, from applying theorem 1, you find the eigenvector. So then you can, so this is, if you generate the subspace by this vector, it will be invariant. So it will be G invariant subspace. So you take the projection from V to this invariant subspace, and you take V2 tilde, the eigenvector of in this quotient. So so I just am repeating what we have done. So you can take the lift V2 to be the element in V such that pi 1 of V 2 tilde, pi 1 of V is just V2 tilde. And then you are just picking. So you do it with putting the index I here. So I plus 1, I plus 1. I plus 1, just a second. And here instead of VI, I put just VI to be the linear span of V1, etc. VI. And I notice that this, if you this subspace is invariant, so if you by induction, so since VI it is G invariant, so the I plus 1 is G invariant, so the subspace in in so put. So if you have the subspace which is G invariant here, so the vector space. So if you span the subspace by V I plus 1, it will be also G invariant. Then pre-image. Yeah. So the subspace Vi plus 1, which is pre-image of. Also, we can notice that Vi plus 1 is pre-image of Pi of Vi plus 1 tilde, where Pi is projection to V mod Vi. So this pre-image of invariant vector space under the G equivariant map is also invariant, is also G invariant. So what we have obtained the flag, so the collection of vectors, the collection of vector space with the basis. So here it is V1. So here it is V1, V2, V1, V2, V3. So the last one, V1, Vk. And so we have obtained these inclusions of vector spaces, and G of Vi sits inside Vi. So G, all elements of, so for any element of G. So this gives you that the matrix is triangular in the corresponding basis. Yes, so that G is triangular. Yeah, so this I just have repeated the previous, the argument that we already have used, yeah, to construct the common basis for collection of. So to construct the triangular basis for the collection of commuting operators, but here what we used is only knowing that this vector is G invariant. Yeah, so and what about the theorem? So notice that yeah, so there is a notion of irreducible representation. Yeah, so just we say that V is irreducible if it doesn't contain invariant, not contain invariant subspace. Yeah? G invariant subspace. So I mean, if you want to find this eigenvector, it doesn't matter which where you are finding it, because because you can do the following. So if you have, so you can pick just yeah, so this is definition. So you can pick. So suppose V is not irreducible. So assume V is not reducible.
If you want to say like irreducible G vector space.
Irreducible G vector space, yeah.
So you want to say that we may assume that V is irreducible?
Yes, I want to say that if it's not reducible, you can take a proper subspace and until the dimension just until this could be either just one vector or irreducible subspace. Yes, so just use and we can pass to the subspace. U until it is irreducible.
And do for this semi-invariant.
Yeah, and then you want to find what you have. So that means that G now acts on U by linear transformation. So you map. So this is not this is not injection, but this is homomorphism of G into GLV of U. Yeah. But so we can find the eigenvector
We are searching for some kind of eigenvalue. I don't know. Could you
по-русски спросите.
вообще я, видимо, отвлеклась. Сначала
Да.
по определению приводим представление, а потом что с этим делать?
Не, ну вот это было определение неприводимого представления, а потом утверждается следующее, что мы вместо того, чтобы искать собственный вектор внутри V, можно искать вектор внутри инвариантного подпространства. Ну, так сказать, поскольку можно все, брать все более и более маленькие инвариантное подпространство, можно считать, что U неприводимо.
So any irreducible representation is one-dimensional.
No, it can. Yes, that is a corollary of this theorem. Yes, so the corollary of this theorem is that any reducible representation is one-dimensional. But in our case, we are planning to prove that G acts as a constant scalar on this vector space.
It's not obvious corollary, yes.
It's obvious corollary because this says that any representation has one-dimensional invariant subspace.
G will be image of this representation as a map from something to GLV.
Yes, yes. Mm-hmm.
Is it so that solvability of a group implies some properties on the representation of this group? I mean,
Yes. In particular, as it was said, that irreducible representations of solvable groups are just one-dimensional.
Because images of solvable groups are solvable groups.
Because, I mean, if you have irreducible representation, you apply this theorem and you get that you have eigenvector,
And we are
which is invariant subspace. So it should coincide with V itself. Yeah?
we are applying this theorem to image of G under representation map.
Yes, we apply. Yeah, so that's why I'm making these comments that we can find the eigenvectors for phi of G inside GL of U,
Was this phi of G solvable?
and this is also solvable. Yeah, so this the homomorphism of solvable group was solvable. And algebraic. However, I could formulate from the beginning, so that this theorem was homomorphism. So then it will be less clear why I'm doing this, but this would avoid this step. So this step will be just more or less automatic. So this eigenvector, eigenvector in U, of course, gives U eigenvector. It is also eigenvector in V. Yeah? So yeah, so then you do the following. So then why we're using solvable groups? Just to use the induction. Yeah, so induction. And notice that induction says, induction on dimension of V, of G. And of course, since we have already proved that commutant is algebraic subgroup, so algebraic subgroup, if G is connected, then this group is connected, and it has dimension strictly less than G. So dimension of the commutant is strictly less than dimension of G. So this then we can apply, of course, induction to the action of G acts on U, and has an eigenvector there. Yeah, so just acts by scalars. Yeah? Act by scalar on V that belongs to U. And then you can consider the eigenspace. Yeah? So you can consider, so notice that, so you have a character chi. Yeah? So let us let us recall the following lemma. Suppose you have H is a normal subgroup. So H, you have chi is a character, so it is homomorphism from H into K star, so this is character. And we have already more or less done this. So for V, we have considered V chi. So G sits in the linear transformation of V. And for so we can consider V chi, so the set of vectors of V such that H of H applied to V is just chi of H of V. And notice that we have proved that if you apply G to this V chi, so this is equal to the eigenspace of the character where just of the character tilde. So we proved that where chi tilde is just the character of, well, where chi tilde of H, it is, yeah, so I do not remember if inverse is here or here. So I think here, but it can happen that this is not the case. So the character is this one, so this different one. And notice that if you have, Vk, if you take Vk and Vk tilde, so these spaces clearly do not intersect if the functions are different. Yeah, so if chi is not equal to chi tilde, and moreover, if so, these vectors are linearly independent. So the just if you consider the sum, so if you have collection of pairwise different characters, so if you have a collection of chi I is not equal to chi j, so then the sum of the direct sum of this vector space is equal to the sum of the spaces inside V. So I can pick up different spaces V chi I inside V. And I can form their sum. And since the vectors with different eigenvalues are linearly independent, then the sum of these spaces is equal to the direct sum of the spaces is actually equal to the sum of the subspaces inside V. Yeah? So this shows that there are only finite number of such chi's. So for a given vector space, there are only finite number of such chi's of chi i's such that V chi I is not empty, so it's not zero, and G permutes them. Yes, so G permutes them. So this tells you that just you get the map of G to the group of so if you have chi1, etc., chi k, the set of all characters just that such that V chi I sits in V and not equal to 0, then you have the map just of G to permutation group of over these elements. Yes, so this is rho is an algebraic homomorphism to permutation group.
Are we still talking about lemma?
Не, ну лемма как бы мы доказывали уже. Ну как бы это просто вычисление, да? Нет, я просто говорю о редукции, ну вот в условиях лемма. So I'm talking in conditions of the lemma.
Вот
Да.
утверждение леммы.
Нет, ну утверждение лемма было вот здесь. Так. Я забыл. Не, в смысле, да. Вот здесь. Ну что, когда мы действуем элементом G на VH, да, то мы попадаем в другое представление с другим характером H. Ну, вот это представление, ну, в смысле, это то подпространство, где H есть. Да, снова собственный вектор для всех H, но с другим характером.
Кажется,
Ну, а? Ну да, мне тоже кажется, что правильно, но...
У нас есть какой-то вектор.
Ну, давайте тут не будем проверять, потому что, более того, потому что я помню, что я это делал на видео, так что, конечно, это, так сказать, не аргумент, но иногда, вот.
У нас тоже.
А?
В смысле, на видео.
У нас здесь, не вообще, ну как бы. Вот, но это тоже, так сказать, аргумент по поводу разных фильмов, что где-то Человек-паук уже снимался. Вот зачем смотреть еще один фильм? Вот, ну, в общем, короче говоря, if you have the so now we can consider all possible eigenvectors that all eigenspaces that can occur in V for different characters. Yeah, so then you have the finite set. This set is finite because we have already, by the way, discussed it. Yes, so that you can bound the number of factors by the dimension of V here. Yeah? Because this is a direct sum inside V. And this tells you that our group permutes this vector space. But so in our theorem, so now let us apply this to our theorem. Just put H to be the commutant. So apply this for H equal to commutant. And the vector space for this eigenvalue. So this means that you will map G maps to the permutation group. Yeah? So the corresponding permutation group that permutes the corresponding factors psi I. Yeah, so that you have this subset of psi I inside V, and when you act by the elements of G, it permutes the factors. Yeah? So that's why you have the map to permutation group. And so since G is connected, the morphism is trivial. And this implies that G simply acts on just on V chi. So you notice that just on some V chi trivially. Yeah? So I mean G maps V chi to V chi. Yeah? So just not trivially, but G of V chi maps to V chi. But notice,
You say that it's always like this, but
нет, ну тут были с разными характерами, а тут я говорю, что раз группа G связана, а эта группа перестановок, она конечная, то дискретная, тогда вы получаете, что so this means that the morphism is trivial. Yeah, rho is trivial. So morphism rho is trivial. So this means that G fixes all the components, all the VKs. Yeah?
so and why we can't say same thing here?
Чего?
Because we need connected group.
Connected group, да.
Real theory is morphism of algebraic groups.
Hmm?
Real theory from G to the
Is morphism. Is a morphism of algebraic groups. So as we discussed, so it is homomorphism of algebraic groups. Since sigma k is finite. Yeah, so G maps Vk into itself, and you notice that Vk is invariant with respect to H. Yeah, so is H invariant. And also, we know that H acts, so H acts by the scalar, yeah, so on Vk by the scalar. So let us look at the following. So now we can consider the images. So Vk becomes the representation of G, and consider the map of G into GL Vk.
What do you mean when you say that H acts on the VK by the scale?
Ну, вот это.
By different scalars, different.
Но она все вектора растягивает на один и тот же элемент. Да? То есть, если вы берете фиксированный элемент H, so if you, yeah, so by the scalars, yeah, so just so each element H acts on V by multiplying of the corresponding by the corresponding character. Yeah? So this character, of course, depends on H. So, but notice that you can put now this phi tilde is a homomorphism. So notice that phi tilde of H is just scalar matrices. So scalar matrices. And elements of G. So this means that we can assume that so it acts by scalar matrices, and so the last point is the following. So you can apply so now we have to recall that V is, from the beginning, we have assumed that V is, it acts by scalar matrices, so in particular it sits in the center of G. Yeah? So, the thing is that this scalar can be different. They can depend on, so this character can depend on the element of H. But then we notice that Vk is just, it is a representation of G. We assumed that Vk was sitting in U irreducible representation. Vk is irreducible itself. And yeah. And what about this? Now we have to use that we are working with commutant. Yeah, so now let us let us recall that H is a commutator. So it is a commutant of the group G. Yeah, so recall this fact. And then you can understand what is the character. Yes, so if H just acts like if you have so before, I mean before just when we talked about G sitting in GLU, if we talked about G sitting in GLV chi, and here we are thinking of the commutant, so let us redenote them by the images. Yes, so denote the images again by phi, again by G. Yeah, so of course, I'm speaking about, so here you are speaking about the image of G in this group. Yeah, so without loss of generality, we can put the images of G and, so let me just write it down. So you have this image in the matrices and commutant, but then you can consider determinant of, so if you have G here, so G is written as G1, G1 inverse, G2 inverse, and well, you're taking all those products, yeah, so of such elements. Yeah. So you can take the determinant of G and see that this determinant is equal to 1. Yes, so just this determinant is equal to 1. Yeah. Okay.
Repeat what are we doing now?
So I want to understand something about this character. Yeah, so what values can we have? So какие значения может принимать эта функция, этот характер? I want to get the values that the character can have. And in order to do this, I just look at the image of G here and recall that if you have if you have the element of H that belongs to the commutator of G, then the determinant of H is just 1, yeah, because for the evident reasons. Yeah? And then you get that H acts by scalar matrices, yeah, so by this character, and on the vector space V chi. And the determinant is equal to 1. So this, so you have H acts on V chi by the following. So you are just writing down chi of H on the diagonal. And the determinant of such matrix is equal to 1. So this implies that chi of H to the power n is equal to 1. Yeah?
What is pi?
Где? P – произведение. Ну как, просто коммутант – это произведение коммутаторов.
It's product by I.
Да. Хорошо? Ну, просто потому что H — это произведение коммутаторов, ее определитель равен 1. Ну, потому что они коммутируют и сокращаются. Because they commute and cancel. Yeah? Okay? So I get the H acts on Vk diagonally. So this implies, since the determinant is 1, this defines that chi of H is equal to 1. Yeah? Yeah, to the nth power is equal to 1. But over any field, so since we fix n, so there are only finite number of roots of unity. So chi of H attains finite number of values.
And is H connected?
Yes. And the H is connected because it is commutant. Yeah. So H is H is not a subgroup. H is the image of the commutant. But this group is connected because we have it is image of the elements written as in this product.
It's not image, it's group generated.
It's group generated by the image, but it is image of some, it's closure of the image of some map of a lot of factors of G. Yeah?
I don't understand what is map.
Just a second. Но это просто мы даже доказывали, поэтому я как бы удивляюсь, что в прошлый раз вы поняли, поэтому. So just notice that you have a natural map here, just picking up G1I, G11, G12, G21, etc., G1I, G2I, and the collection of these elements map to the product. So to precisely this product. And we have proved that it's enough to take a finite number of factors here and take the closure. And take the closure. But but already we know that the group generated by sufficiently many elements is closed. So this product will be closed. And irreducible, so just...
Group generated by sufficiently many elements is closed.
Нет, ну в смысле, что образ этого отображения будет группой, да? Ну, в смысле, что... Но если бы тут было, so if you had so the thing is that the image of the set will be reducible. So it is the image of a reducible set. So the closure of that set will be also irreducible. Ну, потому что если бы у вас было там, две компоненты замкнутых, то вы бы могли взять прообраз одной из них, и это дало бы неприводимую компоненту здесь. Но это множество неприводимо.
Это значит, что для любого количества то, что будет справа, будет неприводимым?
Ну, вот здесь это неприводимо. Ну да, ну и образ любого количества неприводим. Оно не будет подгруппой, но оно будет открытым подмножеством в подгруппе. Если мы знаем, что оно его порождает, если это открытое подмножество подгруппу порождает, то тогда мы знаем, что в каждой компоненте должен быть.
Утверждение, что там правда порождает? Было ли утверждение, что...
Нет, оно порождает. Ну, в смысле, что вот это вот, это произведение, оно именно порождает.
А если мы возьмем две группы, то, в смысле, из G на G просто предложение, которое
Не, ну можно как бы взять еще элементов, тогда оно просто совпадает.
Нет, нам просто вопрос такой, вот если мы возьмем
Не, ну просто
Отображение в G.
если открытое множество, просто вспомните, было утверждение, что если в G вы взяли открытое подмножество, то произведение его на себя уже совпадает со всей группой. Если вы взяли плотное подмножество, плотное конструктивное подмножество в G, то его произведение на себя уже совпадает со всей группой. Поэтому вот это уже вот это множество уже будет совпадать с подгруппой, им порожденной.
So there was like two propositions, this one and other one, that if we are taking sufficiently many J's, then it will be dense.
Да.
And why it will be dense?
Ну, это мы показывали. Ну, да, там было...
Вы показываете конкретно для этого существенным фактором?
Нет, там была общая теорема, где в группе брались набор подгрупп, содержащих единицу. Помните, было утверждение, что если в группе G есть, в нее отображается набор подгрупп так, что образы содержат единицу, то тогда то, что они порождают, неприводимо.
Хорошо.
Вот у вас есть набор подгрупп, которые отображаются в G, произведением, и содержат единицу, значит, то, что они порождают, неприводимо.
Набор подгрупп, в смысле, которые пары G на G.
Набор подгрупп вы просто можете, вот этих групп, G,
Вот эти группы
G.
для разной длины.
А?
Для разной длины количества точек.
В смысле, что у вас есть бесконечный набор, возможно, групп G,
У нас есть бесконечный набор.
и набор отображений, которые содержат единичный элемент в группе G.
Ну да.
Если вот эти вот группы неприводимы, то их образ порождает подгруппу и замкнутую, и вы можете выбрать только конечное число элементов из них. Да, прям так и звучало. So, but what is important is that this is just this is just a number, yeah. So this is raising to the power n. So xh attains finite, so less or equal than n values in k. Yeah? And this is algebraic map. So this gives you that if you applied chi to h, so it will map to the roots of unity. So nth roots of unity. Нет, вот нормально как раз может, а вот коммутант нет. То есть здесь я воспользовался все-таки, что у меня еще дополнительной структуры нет.
Это мы про разрешимую группу говорим?
Да, теперь мы уже вернулись к...
Разрешимые характеры нормально.
Не обязательно, они разные. Но вот для этой h мы попали в корни из единицы. So we're mapped to the roots of unity, and this is finite set. This is just to the element h, I associated chi of h. But h is connected. So h is connected. So this is just only trivial value. Yes, for unit you have the unit value. So chi of e is equal to 1. So that means that chi of h is just equal to 1 identically. Yeah? And now it's all actually. Because now we can apply induction. So now you have the action of G. So you have G and you have commutant. And you see that commutant acts on, commutant acts on VK with a trivial character. So trivial, simply by this corollary. And this implies that G acts on chi via G mod the commutant. And you know that since this group is not equal to this group, so which has small dimension. So this means that there exists.
And what means group acts on other group via?
No, via its factor. Yes. So just if this means that the action doesn't depend on. I mean, that if you look on the corresponding homomorphism, it factors through G mod commutant. Because commutant acts trivial.
Is it okay that it doesn't work for abelian groups?
В смысле?
Well, then,
Ну, коммутант нулевой.
trivial and dimension of G is G modular constant isn't less than dimension of G.
Мы уже отдельно умеем для Algebraic Groups искать.
Да, ну, нет, ну, нет, ну, как бы, поэтому тут надо не индукцию применять, а предыдущую теорему от реагонализации коммутирующих операторов. Так что спасибо, тут вы правы. So we have to apply now not induction. Not two cases. So you recall that this is already a abelian group. So this is a abelian group. And this really tells you that G, by induction, this group can be trigonalized. So by the theorem we have proved. There exists a common eigenvector. То есть поймали вы меня, конечно, но не совсем. Ну, разрешимость нам нужна на первом шаге, но чтобы перейти к коммутанту, значит, это, собственно, ну, подгруппа. Ну,
Сейчас то, что это не подгруппа, а то, что он...
Что она с G не совпадает. Ну, как бы первый шаг ломается, если это совпадает с G. Это,
Где вы используете, что не совпадает?
Просто использовали вы вот весь ряд этот или нет? Или только первый?
Нет, мы использовали только, что вот это разрешимое, поэтому по индукции мы нашли собственный вектор. Ну, чтобы рассматривать вейхи, вам надо... Да, вам нужно... Ну да, просто вейхи не пусто. So we used that this is solvable and not equal to G for proving that Vk is not empty. So, and of course, yes, so the last step follows from the corresponding theorem for abelian group. You cannot avoid just the case of abelian groups. It is not a thematic. So that's why I was talking about that theorem of diagonalization of commutative operators. Notice that here you so here in this statement you didn't use any connectivity assumption. so here. But you used it several times, so here for acting on different VKs, and here for knowing what is the character. Yeah, so what was essential here to see that commutant acts trivially on this character. Yeah? Yeah, so there is, ну, наверное, уже заканчивать, да, пора?
Можете еще сказать, что будет на следующей неделе?
Yeah, so next time I plan to, спасибо, разрешили. Next time I plan to talk about Borel fixed point theorem and some rigidity theorem. Yes, yes. Yeah. Нет, я вообще, я хотел лекцию читать. Ну да. Не, у нас мидтерма не будет, не волнуйтесь. Я его просто выдам скоро, но да, просто листок. Yeah, so there won't be a practical midterm, just I shall only give you the sheet of problems.
А можно совещаться на своими однокурсниками?
Да, конечно. Не, ну,
Спасибо, разрешили.
ну как бы, не, ну знаете, мы все-таки не можем запретить то, что мы не можем контролировать. Мы, конечно, запретим, ну как бы, мы, конечно, можем запретить, но будем выглядеть полными идиотами, правильно? Ну как бы, ладно. Ага, спасибо. Спасибо большое за камеру.